Let's get into, let's see, Martin is here. Great. Martin came in the door having been lost in this, this amazing wilderness of freeways. So I hope you're ready. Martin Odersky, we've known each other for a long time, a little bit. Martin worked on Java generics way back when. I think the Oracle Java compiler is still derived from something you did way back then. And having made his name there, he made his name even bigger by making his own wildly popular programming language called Scala, which is developed at EPFL. Can you say that in French?
École Polytechnique Fédérale de Lausanne.
In Switzerland. And Scala is sort of really, by many people, being perceived as the great alternative to Java. So it's going to be really interesting to hear Martin's keynote today. I'm very grateful that you would come and do that for us. So without further ado, let's move into the keynote and talk to you in a bit.
Thank you. Can you hear me? Okay. Well, thank you very much for inviting me to give this keynote talk here. I'm going to talk about a topic which is something very new that we've done. It's about reflection and compilation. And of course, you could say that's a bit rich if the guy who wrote all the seminal papers, Gilad Bracha, is in the room. Are we not just retracing his steps here? The answer is actually no. There's something else that we bring to the equation if we look at statically typed languages. So what do static typing add to the equation of reflection and compilation? It's something very new. It will come out in the next version of Scala. I was in a bit of a rush to write the slides. I apologize. So they hopefully will be finally finished on 2nd April 2001. The guy here, do you recognize him here? That's Baron von Münchhausen. He's also a German, and he was famous for pulling himself out of a swamp by his own hair. And that's a little bit what we're going to do also when it comes to reflection and macros. Okay, so the talk has two parts. The first talk is what can compilers do for reflection, because it turns out that a lot of code is shared. And the second half of the talk then will be what can reflection do for compilers. So what can compilers do for reflection? In Scala, it's really all about cakes, and you're going to find out what that means a bit later. So as a first approximation, we see that compilers and reflection really do largely the same things. So they both deal with types and symbols for classes and methods and the like. Their names, their trees, syntax trees that you might want to explore from both, their annotations, and so on. And they both answer also similar questions. For instance, what are the members of a class or a type? That's what a compiler needs to know. That's what you would like to know from reflection as well. What are the types of the members of some basic types? That's not the same as just the type that the members are given, but you have to typically do some type computation, at least in a richer type system that has things like generics. Are two types compatible with each other? Is a method applicable to some arguments? So all these things you want to find out in reflection, and of course the compiler knows them as well. And furthermore, in a rich type system, answering these questions is actually pretty subtle. Requires some deep algorithms of subtyping, base types, membership, and so on. But there are also some differences. So if we look at the compilers and reflection, what the differences would be, well, compilers get their info from source files and class files, whereas reflection relies typically on the underlying VM info. It's true that typically the VM reads the same class files, but once you write your reflection layer, these class files are no longer accessible. The VM abstracts them somehow. Compilers generate code, whereas with reflection you might want to invoke code that's pre-generated. So generate code versus run code. Compilers produce error messages, whereas reflection just throws exception if something's wrong. Compilers are typically single-threaded, and that means you don't need to make sure that things are thread-safe. That's no longer true for reflection. Reflection can be called from many threads at once, so you have to make sure that the basic operations are thread-safe. And in compilers, at least in the Scala compiler, the types of symbols very much depend on the phase you're in. For instance, very early on in the compilation process, the types are the Scala types, and then at some point later in the compilation process, the types start to resemble much more the Java types, which are different and generally not as rich as the Scala types. So this progression is not present in reflection, where the types are just, if you pick Scala reflection, then you want the Scala types, but you will not find out the types at some later phase in the compilation process. Okay, sorry. So what can you do for reflection in Scala 2.10? So here's some of the things that we do. So it's mirror-based, following the master. So you get a reflection mirror. That's the standard mirror of reflection. Then you can say, get me the symbol for a name. Give me the class for a name. Well, why don't I just do it directly on the REPL to show you? I would have liked to do this with Donna Malayeri's very nice Eclipse plugin that gives you a sort of interpreter on Eclipse, but unfortunately I haven't wired it up yet sufficiently that it can make use of reflection, because it's in a separate jar and I wasn't able to figure out how to put that into Eclipse. Okay, so let's see what we do. So we say import Scala reflect.mirror. Well, let me maybe just do a named import. That means that let me do something else. Let me do a named import. Sorry? Okay, I can do that. 1 second. Okay, so now we have a mirror that's called M, because I used an import that renamed it. What I can do now is I can say val f equals m dot symbol for name of, let's pick the type Scala function 1. Okay, so we have a class. Let me just write an instance of that class, a non-trivial instance of the class, a vector. That's a data structure, so that's indirectly a function. Sequences are functions. So what I do now is I want to find out the type of that instance, so call that vt equals m dot type of instance v. Okay, so it says that's a reflect mirror type. It's an immutable vector. Then I could say, well, what's actually the type at the superclass? So that says, well, base type is essentially to say, well, that type here that I started with, what's its type seen as a superclass? And it tells me correctly it's a function from int to a, where a is the element type of the collection. So it was smart enough to substitute int for the first parameter of the function. Okay, I could then do vt dot members. Let's see what we have here. Oops. Sorry. Okay, there we go. So we get a large number of members. Let's do something else. Functions have fewer members. Oh, sorry, f dot s type members. Okay, so that's the members of functions. I could also say vt member of new term name apply. So it says, well, give me the m dot new term name. That's another mirror operation. So that gives me the apply method in my function. That's what this thing does here. So here, what you see here in Scala, we actually have two name universes. We have names for terms and we have names for types. So a string is actually not good enough because it's ambiguous. So we have to say, well, I want the term name for that, or I want the type name for that. Okay, so that gives me the apply method. Let's find out what the type signature of the apply is. Sorry, that was res9. Or let me do val apply equals res9. I forgot to give it an result. Okay. Okay, so it says, well, it's an index int to a. So what you see is that the type signature of apply is already instantiated with the correct type here. So I think you got an general image view of what one can do. One can, of course, also do the usual things like invoke methods and select get fields, set fields, and so on. Okay, so I said reflection was mirror-based. So what's a mirror? A mirror is an object that can return reflective information about runtime values. So we use the mirror to get, for instance, the symbol of a class, or to get the type of a runtime value, and things like that. So in Scala, a mirror contains everything needed to describe the reflective informations. That means mirrors define types for symbols, for types, for names, for annotations, for trees, everything. So all the core types of reflection are nested classes inside this mirror. And what's more, and I think that's where we depart a little bit from the dynamic view, if you have different mirrors, then these mirrors are, the types in these mirrors are incompatible. So if you have a mirror, let's say reflect mirror, that's our standard mirror, then the symbol class in that mirror is actually incompatible from, let's say, a remote mirror that would look at a different VM and look at those symbols. That's generally good practice because these types are generally not interchangeable. So you don't want to confuse them. If you do want to have a common supertype, then it would be this one here, where we say all these mirrors, their type is actually called reflect API universe, so that's the universe that contains everything, and then the hash just says, well, give me the symbol type in that, forgetting which precise instance it was. So here we still remember the instances, here we forget them. These things down here are called path-dependent types, and they're one of the cornerstones of what we do in Scala. Okay. Yeah, that was the reflection view. Okay, so if we look at how to implement this stuff then actually there's quite a lot to do. So in Scala alone, to represent the trees, we have about 40 classes to do that. There are about 5 classes for symbols, about 10 classes for types, 2 for names, type names and term names, I said that. And then we also have to do all the essential methods that decompose these classes, explore relationships like X subtype of Y, members of X, and so on. And that's roughly equivalent to what we would write in a language spec. And it's also, of course, roughly equivalent to what a compiler does. This is the core part of a compiler. That's the job of essentially the core type checking abstractions in a compiler. Okay, so we would like to reuse it. So let's see what others have done. So here, let us look at what Java has done. So we have a type in Java. It's called Java lang reflect type. And it has nice subtypes that tell us what a type can be. It can be a generic array type or a parameterized type or a type variable or a wildcard type. And then, of course, it can also be a class. So that's typically what the types in Java are. And then we say, okay, great, let's look what we can do with these types. So let's open the interface type. And what we see, it's completely empty. There's nothing in type, nothing whatsoever. And if you go and say, well, maybe there's something in the sub-interfaces, then we see each one of them essentially tells us what it is. So, for instance, if you have a parameterized type, it would tell us, well, these are my type arguments, and that's it. It doesn't tell you anything more. So, want to know whether type A conforms to type B in that? Write your own Java compiler. If reflection won't help you there. It won't expose these things. So why not add more meaningful operations? Isn't that criminal of the language of the designers of Reflection 1.5? Well, it's actually not so easy. Because what you need to do is, like I said, you need to write the essential parts of a compiler to do that. And then furthermore, down the road, you need to ensure that your reflection compiler corresponds bit for bit to the latest version of your language compiler. And that's almost impossible to maintain unless you really share the code between the two. Otherwise, you have 2 compilers, and, well, a bug fix in one would change the behavior that has to be reproduced exactly in the other. It would be a nightmare. So that, I believe, is the reason why Java in 1.5 actually deviated from the 1.4 model. In 1.4, you could find out all the essential things about a type, like the superclasses, the interfaces, and you could find out whether a class is a subclass of another. That's the core operations. But the Java 1.4 type system was very, very simple. So it wasn't a big deal to actually duplicate that in reflection. with the Java type 5 system, Java 5 type system, that's no longer true. And therefore, the designers of reflection have said, well, that's too much for us. Let's not go in there. Let's just give this very simple view that tells you the types, and that's all. Okay, so the problem then is how to manage dependencies between compiler and reflection. And a core way to manage dependencies is dependency injection. So let's have a look at dependency injection again. Of course, that's something that's quite popular nowadays. There are a number of frameworks. So the idea is we want to avoid hard dependencies between specific classes. Instead, we want, of calling specific classes with new, we want to have someone else to do the wiring. No hard links. Again, Newspeak, of course, is the most radical, exemplary of that philosophy. Okay, so what I do here is I use a standard solution, that's Google Juice. So here's what you would do to do that. So here's a typical example of a service interface where you say you have an on-off device which has a on and off. They're both unit methods. You have a sensor device that tells us whether coffee is present, and you have a warmer that you can trigger. And then you have implementations of these things over here, where you say you have a heater which has some mock implementation, a pot sensor that tells us whether coffee is present, and then we have a warmer that has a pot sensor and a heater and extends the interface here. And what we then do is we have the client that says, well, warmer.trigger. And now, of course, what we have to do is we still have to make sure that these are, whenever we want to have an instance of these, we get one of these. So nobody tells us that. So that's what the dependency injection framework does for that. And all it needs is that we set it up with a little bit of boilerplate, well, actually quite a lot of boilerplate, that tells us, well, these are the dependencies. That's what I need to do. Okay, so that's sort of one of the standard ways, Google Juice. In Scala, it's actually built in. It is actually a consequence of this idea of path-dependent types and self-types. So let's see how we would do the same thing in Scala. So what we would do is we would have the same service interfaces as before, and then we would have the implementations as before. But what we would do now is these implementations, they would have the links to the other components as values, as abstract values. The warmer component would just say, well, there is an on-off device. I don't know what it is. Let me just specify that as an abstract value. And there is a sensor device, and that goes here. And then, of course, because it's specified what they are, they can talk about these things. And then in a client, I just have to instantiate all these guys. I have to say the on-off device is a heater, the sensor is a pot sensor, the warmer is a warmer, and I'm ready to trigger the warmer and get some coffee. And what I can also do is I can have an object that refines this thing, call it test here, that says, well, I make a new client and I override some of these value definitions where I would have a mock heater and a mock sensor, let's say, for testing. So I still have all the flexibility of dependency injection, but I have it in the language. I don't need to do bytecode or source rewriting to get there. Okay, so that was a very simple case because there was no cyclic dependencies between the components. Oh, sorry, to sum up, so in the Scala model then, components are classes or traits. Requirements here are abstract values. We'll see in a second another way to express them. And wiring is by implementing the required values, like that one here. But what about cyclic dependencies? So cyclic dependencies, it's not so easy anymore. So what we do there is start with the service interfaces. And what we do then is we have three traits, the warmer component, the sensor component, and the heater component. And they each define their class as a nested class. So warmer component would be a warmer, sensor component a sensor, and so on. And they also define an instance of the class immediately in here. So where we would say, well, that's the warmer, that's the sensor, that's the heater. So since they're all separate, how can they talk about each other? How can they find each other? Well, that they do by specifying the type of this. So this is the type of normally the type of the enclosing class, but in Scala you can make this basically be anything. So we say, well, this must be the type of this assembly. the whole assembly. So what is assembly? Well, we say assembly would be a trait that extends these three components, and that's all. So we would say, well, we want to be a part of all these three components. And then the client would just extend assembly. There would be nothing more to do in wiring. It could go on right away and trigger the warmer. So components in this model are still traits. Wiring is now by mix-in composition, and requirements, and that's the important part, are the types of this. So a warmer component can say, well, the type of this of myself is an assembly, which is something larger than myself. That means that I need to be mixed into something that's at least as good as an assembly. It could be assembly, it could be a subtype of assembly, but assembly is the minimal requirement for the type of this here. The width is mix-in composition. So it just says, well, take that and that and that, take those traits and mix them together. So that has been called the cake pattern. I think it's the cake pattern because you say, well, each one of these is a slice that you put together, and each of these slices can have actually nested classes. So these would be the layers of the cake that they say the mix-in gets, these nested classes get mixed together all in one big cake. Okay, so in fact, the cake pattern is pretty ubiquitous in Scala programs, at least in a lot of the more complicated Scala programs follow it, so including the compiler. So the compiler is essentially one big cake. If we look at the parts of the compiler, like types or symbols, then they're each in their own slice. So we would have a trait types, which has a class type, and then, of course, it would also have subclasses of type, like method types. It would have a list of symbols and a result type. And then we would have a class of symbol, and it has at least a field type, and of course many other things like that. And they can talk about each other. So here we can refer to symbol, and here we can back refer to type, because the self-type is in all cases symbol table, and symbol table is the cake that unifies everything, that extends all the other components. There was a question. The self renames the this. So you can give it a name. You can say, I want to talk about essentially the outer this, what you would say in Java symbols.this. I can give it a name, a shorter name. If you don't do that, just write this, and that means, well, I can refer to this only with this. So it's an optional way to give you a name for this outer this pointer. Okay, so with that, with those preliminaries, the question is now, can we unify the core parts of compilers and reflections? So I said already they are really yin and yang. They're very, very close to each other, but they also have some different requirements. So one way to do it would be to say, well, we know that compilers are cakes. I've already alluded that reflections are cakes. So can we take these two cake patterns and just make a common super cake? So there would be a type in here, and there would be a type in here, and then they could both inherit from the type of this cake here that would somehow combine the commonalities. So that's the first approach. There's one problem with that, and that it exposes way too much detail. So if you have this common super cake, then that's still not really for public consumption, because it's essentially, it abstracts out everything that can be used in reflection as well as in compilers, but it would typically be fairly low level. It would export things that are used for the implementations of the compilers and the implementations of the reflections, not necessarily the API. So what we do instead is we put another cake on top of it, and that cake now is the cleaned up facade, which is usable from the users. And that cake is called Reflect API Universe, and its standard instance is Reflect Mirror. So the mirror Reflect has the type Reflect API Universe. And that the implementation view of that then would be Reflect Internal Universe, and that would have two subcakes. The Reflect Runtime Mirror, that's the actual one that does all the work of the reflection mirrors, and NSC Global. NSC stands for New Scala Compiler. It's the current standard Scala compiler. And global is essentially the root of it, which is the mirror here. Okay, so what does this facade look like? So here's a small view of that, what we do in the facade. So that would be the trait types that explains what a type is. So one thing we need to do is we have to expose things in the API that you might want to do about a type. So you might want to find out, for instance, member. That was an operation we have used. It gets a name and gives you back a symbol. There are also all members. That gives you all the members. There's a subtype operation, less than, colon, less than. There's base type, which is also used. So those are sort of the sanitized operations that we would like to expose from types. But the type itself is, of course, much richer than that. It would have also lots of operations that are internal to both the reflection and the compiler algorithm, which are the same algorithms after all. So we have an abstract type here. Type is a subtype of abs type. And then in the same thing in Scala reflect internals, we have this type types. Now that's the implementation. And it extends reflect API types. So that's this guy here. And that means we need to give a definition of the abstract type. So that goes here. So there would be a class, actually an abstract class. Type extends that guy here with all the implementations of the thing. Couldn't we just have used interfaces? That's actually, interfaces are actually not enough, mainly for that thing here. So here we, in the abstract view, we actually refer to the abstract types also in parameters of these methods. And to be able to implement them, we need to know the concrete view, the implementation view, because the abstract view is not strong enough to actually do all the implementation work. So of course we could just take the user level type and cast it to the internal type, because at runtime it would be that, but we all know casting is not good, it's not nice, it's error prone, so it's much nicer if the language avoids these casting operations. And these abstract types do that precisely, because type less than abs type just says, well, there is a type, it's a subtype of abs type, and here now I know what it is, and on this level, of course, the compiler also knows what it is, so it will let me invoke all the implementation operation on a type. Okay, so to summarize, the first part then is Scala is a pretty regular language when it comes to composition. It has a couple of unifying principles, namely everything can be nested, classes, methods, objects, types, doesn't matter. Everything can be abstract. Methods can be abstract, of course, but we also have seen values that are abstract and types that are abstract. And furthermore, the type of this can be declared freely and can thus express dependencies. And what I've shown you is that this lets us express a powerful new pattern for software design in the large, which I would call the cake hierarchy, or if you want a different name, you can also call it the wedding cake. So essentially, you have several cakes that extend each other and can also abstract from each other in this situation. And I think it's a very, very powerful pattern. And I think at least from the parameters we started with, namely that represent types in an object-oriented, represent reflection information in an object-oriented way as classes with methods, I think it's the only way to actually achieve that thing. I don't think there's any other thing that would actually achieve similar unification of algorithms and at the same time abstractions. A different way to do this would be if you want to expose essentially just naked data types, and these would be universal, then the problem gets much easier, because then you can essentially hide the algorithms outside the data types. But if you want to have an object-oriented view, then I think that's the only way to do it. Okay. Yes? Yeah. You could definitely parameterize. So there's a trade-off whether we want to parameterize or not. The problem with parameterization is that you have to then, every time you mention the enclosing type, you have to supply the parameter. And sometimes that can be very verbose. Whereas that thing is essentially the binding is name-based, so you can, for a long time in your hierarchy, you can just leave this thing abstract, and by the time you instantiate it, you just give the definition and it's valid everywhere in your hierarchy. For these purposes, I believe that's actually advantageous to do it that way. But otherwise, you're right, yeah. No, there's actually one problem. One technical problem is if you want to parameterize the trait types with type bounded by abs type, you have a problem because abs type is a nested class inside types. So that wouldn't be possible. You can only refer to things outside your trait in the bounds, not to things nested in your trait. But in general, yes, in general, the two are substitutable for each other. Okay? Good. So let me come to part 2. So now we've seen that what compilers can do for reflection. Let's see what reflection can do for compilers once we have it. What happens when a compiler makes use of reflection? Well, it would mean it can call some user-defined methods during the compilation, more specifically during type checking. It can call some methods that the user has defined. It can find them using reflection, invoke them using reflections. So what would you pass into these methods and get out of them? Well, most obvious thing would be the compiler deals with things like trees, explicit syntax trees, and types. So pass them into the method and get them back. And the method would then return with a tree. What that then is, it's a macro system. It's just a very simple macro system that consumes syntax trees and produces syntax trees. And all we need, in addition to the machinery that I've shown you, which has shown you all the types, symbols, trees, whatnot, in the mirror, all the machinery, the additional machinery, the only additional machinery we need is this single reflect call. That we say, well, the compiler is able to use things reflectively. So let's see what that looks like concretely. So here's a prototypical macro definition. That's just, the left-hand side is just a normal method definition in Scala, so there's nothing different from that. And the right-hand side, instead of having a body, it reads macro, and then comes a reference to the macro implementation. So the macro signature is just a plain signature. There's nothing particular about it. The macro implementation then, that must be in a statically accessible object, because we want to call it from reflection. So it can't be, let's say, in a class, because we wouldn't have the object of this class when we call it in the compiler. So let's put this in a top-level object impl then, call it mi for macro implementation, and that then would take a tree and return a tree as a first approximation. So where the original macro definition says, well, I take a value, an expression of type t, where t is int or string or whatever, and I return another one of these user types, int, string. Down here at the macro implementation, they're all trees. They're the syntax trees that the compiler produces for these expressions. Exactly right. Yeah. This one must be separately compiled. This one not. So this one can be compiled with the usage of the macro.
Martin, can you repeat the questions for the recording, please?
Okay. So the question was, then these things must be separately compiled, and the answer is yes. The macro implementation must be separately compiled. The macro definition can be compiled with the caller. Okay. So how would we expand a macro? So here the rule is again very simple. If during type checking the compiler encounters a macro application, let's call that m of expr of some expression, it will expand that application by invoking the corresponding macro, or more precisely, the macro implementation. So it would reflectively call impl.mi. And what does it pass into impl.mi? Well, it passes two arguments. It passes first a context, which contains info about the call side of the macro. For instance, if there was a prefix, a qualifier, you would see that in the context. You would also see line numbers and things like that. And then the second argument would be the AST, the abstract syntax tree, that corresponds to this expression argument. So what then happens is the macro would do its work, and it would hopefully return a tree, and that tree would then be inserted into the calling tree at the point of the macro, and it would replace the macro application, and it would be type checked in turn. So compiler would then go on and type check the application. Of course, the application could contain further macro definitions, and then the process would repeat itself. So here's a simple example. Let's say we have a macro assert. It takes a condition, a Boolean, and a message of any type any, and we would say, well, that's just a macro with assert impl as its implementation. And then when we would call this macro assert with, let's say, x less than 10 and limit exceeded for the arguments, that then would lead at compile time to an invocation of this assert impl, which I haven't shown you yet. And the first argument would be the context, the macro context. And the second argument, second and third arguments would be two abstract syntax trees that stand for these two expressions. Now, in other macro languages, these abstract syntax trees, there's actually a notation for them, quasi-quoting. You can express these quotations. In Scala, that's not the case. So when I write that, that's a meta notation that says, well, that's the abstract syntax tree that corresponds to these things. So in reality, these two syntax trees, they actually would be written like this. So the first one would say, well, it's an application, and then it's a selection where I take a new term name x, new term name, that's what we did with reflection, so you see the things repeat itself. And then I select the less method, so I have to, because it's a symbolic method, I have to write it in escape notation, so that would be $less. And then the arguments of this method would be a constant, which is 10, a literal constant 10. So that's the thing I would have to write. We'll see later on how I can avoid that. And the second one would just be a literal call with a string constant called limit exceeded. Okay. So the implementation of assert then, how would that look? What would that look like? Well, it should be in a globally accessible object called it asserts. And here we would have our assert implementation. So it takes this macro context, it imports from here, and it takes a condition and a message, which are both trees. When I said trees, we have to say, well, wait a moment, trees are part of a mirror. I have to give the mirror. In fact, the mirror comes from the context. So c.expr is essentially a wrapper of a tree in the context universe. So context defines a universe of discourse, which essentially corresponds to the current compilation run. So that's the types that I define in here. And message takes an expression of any, and the result type would be an expression of unit. And then the body of this thing is most straightforward implementation would say, well, if assertions are enabled, then return this syntax tree. We'll see later on how to construct that. Otherwise, return just the unit, empty unit, which corresponds to the empty branch of an if then else. Okay, yeah. How do we track the dependency between, of the implementation of the macro? Right now, we say that's a task of the build system. So there's nothing in the language that would track that for you. There's just a requirement that the implementations get compiled before the call sites where the compiler would finally reflectively invoke them. You don't know the true dependency graph. That's right, because the assert impl call has appeared from the bytecode. Yeah, true. Yeah. Yeah. So when are these expressions expanded? So the answer is the arguments that go into a macro are fully type checked. That means they're also macro expanded. And the result, the tree that is the result of a macro does not need to be type checked, so it will be type checked again at the call site. Here it would be expanded strictly, but you get the lazy behavior by returning a macro from your macro. So that macro will then be expanded again at the call site. So typically you can turn things around. Anders. So the current proposal, which we have formalized for 2.10, not yet, but we definitely intend to do type macros as a next step. Yeah. So to give you some idea of, so the syntax is already specifically so that this would be possible. For a type macro, we would just write type instead of def, and we would define a type name, and we would do the same macro linkage as we would do otherwise. But we haven't neither specified nor implemented that yet. Yep. Good point. Can I take that? Let's go here. Here it's super easy to make a mistake, and the consequences are catastrophic. So that's precisely what I want to get to in the next slides. So that's part of the bootstrapping that I'm going to talk about. Okay. So that was the assert macro. Oh yeah, the other thing I wanted to say is that macros can also be generic, so they can take type parameters. So here we have a very general one. There would be a queryable type, which itself has a type parameter t, and then map would have a type parameter u, and there would be a predicate from a function from t to u, and it would return a queryable of u. And here's the implementation of that thing. So if we look at the implementation, what that actually does is it takes all the type parameters that are defined here, and it labels each of these with the context bound called type tag. What that basically means is it wants to have a runtime structure for these things. So it's like we switch from Java's erase types to .NET's reified types. When I specify type tag in Scala, it says, well, I want to have the runtime type of that. And the compiler will give it to me. So then it takes the context as before, it takes the predicate as before, and it returns the same result as before. So the only new things are these type tags here. So if we expand a generic macro then, let's say q.map of int, then what that actually would happen with the same rules that I've showed you before is we would pass first the context, and then we would pass the actual syntax tree of the thing that we pass in, the closure that we pass in. And then as the last parameter list, there's a list of implicit parameters that give us essentially the runtime types for these type tags. Implicitly is just a simple method in Scala's predef. It's not magic at all. It realizes implicit values, so it's defined like this. Implicitly of t, and we want to get an implicit argument of this type t. Oh, sorry, that's a typo, and we return the argument, the x. So that's implicitly. It just means that if we want to get an implicit value defined on this type. And that what this thing here then means is that we say, well, we want to give you the runtime type, compile time type information for the two parameters, and the first one would be essentially the representation of string, and the second one would be the representation of int. It's equals x, yeah. Okay, so final thing we have to look at would be contexts. So a context then, what is that? So it's an abstract class. The first thing I have to define in a context, I have to define what the universe is, which is essentially the current compiler run. So there we have the mirror in our context universe. And then context contains some other useful information. In particular, when I call here like q.map, in the map method, map implementation, I typically want to know on what it is called. So that's another thing that I put into context. That would be the prefix value in a context. And for good measure, I also get its type, which is an abstract type here. Okay, the final things in the equations are tag types and trees. So I've already talked about expressions and type tags. So what are they? So they are just two very simple case classes, also defined in contexts, where I say an expression wraps just a tree. Again, that's a typo. I apologize. That should just read tree. So instead of the T, it's tree. So it wraps a tree with the type of that tree. It just says, well, an expression of type T, it gets an abstract syntax tree, which don't carry their types around. And here I essentially seal that and says, well, that's the type of the tree. And type tag does the same thing with a type. It just says, well, here's the type T represented by this internal type information of the compiler. And type tags, I said already, can be synthesized by the compiler, which is Scala's mechanisms to get reified types. If you know Scala pre-210, it's called manifests, class manifests and manifests. And now, because we have to make them essentially mirror dependent, essentially a manifest is just a standard type tag in the reflect mirror. But the general abstraction now is called type tag. Okay, so now we come to the problems. So I've been conveniently pushing things under a carpet when I showed you the assert impl implementation, because I was still using this abstract syntax tree notation, which I have admitted Scala doesn't have. So here's the ugly truth. Here's what we would have to write for the syntax tree. So we would say, well, it's an expression, and then it's an if, select cond, and then this unary $bang, that's the not operator on the thing. And then we have, in the then part, we have an application of a new term named identifier raise, and the message, and in the else part, we just have a unary literal constant unit. And it's pretty ugly. But it's also completely wrong. Why is it wrong? What's wrong with this thing? Exactly. You're looking at raise in the namespace where the macro is defined. Raise was a thing that was in the assert impl thing. But it will be type checked at the expansion site, at the user site. So there is no raise, or what's worse is there might be a raise, but it's the wrong one. So we would introduce dynamic scoping where we just get whatever is closest in the call site here. That's not something we want to do. So let me take a quick detour. We get there. So the answer to these problems is in a cute little macro called reify. So reify then is a macro that goes from T to expression of T. So what it does is it takes a tree that represents an expression of type T as argument. That's the normal thing. And what it would give you then is it returns a tree that represents an expression of type expr of T, and that means that it contains a tree that represents the original expression tree. So instead of a tree being an int, let's say, I now return you a tree that, when run, will produce a tree returning an int. Okay? So an easier way to look at this is to say reify. Well, you shouldn't laugh. It's exactly link what we do, right? It's So another way to put it is reify is like time travel. It builds a given tree one stage later. And that's essentially the core idea of link, but now expressed as a macro. So the core idea of link would be make ASTs available at runtime, which is one stage later. Okay, one cool thing that you can do with reify is splicing, because it turns out that actually the eval method on expression and the reify method are inverses of each other. So reify goes from T to expr of T, and eval goes from expr of T to T. And furthermore, we have that equation given, which says, well, if we reify a tree and it doesn't have free variables, so these have to be handled specially, and we evaluate this expression afterwards, we get back the original tree. That's the meaning of reify. When you run this thing, give me back the tree. And what we now postulate in Scala, so that's essentially an implementation decision in reify, is to say we want the other part of this inverse to hold as well. So if we see a call eval on an expr and we reify that, we want to just simply replace that by expr. That means that's the splicing operation. And we say, well, we have this other thing, which could be the result of some other reify, call it with eval, insert it into a tree, and that just means take this tree and splice it. Okay, with that, then I can finally show you how we do assert. So it's the same thing as we've seen before, but here is now how we write that. Say, if assertion's enabled, then we reify the code, if not cond eval, raise message eval. So it's like the original code that you would run, except that you need eval twice. You will here, because cond is an expression, you can't have an expression of Boolean subject to a not operator in an if condition, of course. So you have to evaluate it. That gives you a Boolean, and then you can do that. And here is the same thing with message. What's better about this is that in our experience, these differences between expr and normal things, they help greatly in actually getting things right. Because typically, people get it wrong all the time, but typically it's a type error. You have somehow got in your head the wrong idea of what stage you want to run things. And fortunately, this thing here is tracked by the types. So the types prevent silly mistakes that come from confusing staging times. And the other cool thing here is now this thing is subject to reify. So that means it will be expanded here. Reify is a macro. And then it will be type checked. And when it's type checked here, then raise actually has the right binding. So we have the original binding. So that means that with that thing, we actually can regain hygiene. Yeah. There's no magic whatsoever. So the scope is just this thing here. So right. So you mean so these will be reified. If it's under reify, these will be reified as a free reference. So essentially, yeah. Yeah. Okay. Very good point, yeah. So actually what I haven't shown you the whole truth. Actually, the Expro has two methods. One is called eval, and it will expand by name. So every time I do that, it's by name. And the other is called value, and it will expand only once. But we assume then that essentially the expansion doesn't have any side effects or things like that. So that's why there are two. Because sometimes you do want, let's say, the expression here, the original expression has side effects, then you might want to expand it with the side effect several times, so it would change the semantics if you didn't. But if the expression is pure, then value would avoid the duplication of code. Okay. So to summarize, the second part then is I've shown a classical bootstrap operation. So we started with a super minimalistic macro system. Basically, we already bought into the whole reflection thing, and then all we needed to add was to say, well, we have a minimal way to let the compiler call a method reflectively, passing trees and types in and out. We've seen that macro system was very cumbersome to express syntax trees. It's super powerful. You can do everything with that thing, but it's also very, very cumbersome. And it's also very, very dangerous because by default, you don't have hygiene. What we did then is we expressed reification as a macro in the minimalistic system. And with reify, we get compile time staging. So we can move things to a later stage. And we actually use that at compile time. So what's the interesting thing here is that there are actually two phases here. So there's the phase where we say the expansion time here of the macro, and then the further expansion time when the macro is called, right? So that means that macros calling macros give you another sequence of essentially time steps, staging steps, very much like essentially multi-staging languages give you at runtime where you have multiple stages that you run. With macros, it's sort of time travel ahead rather than time travel backwards in compile time. Sorry. Got too far. Oops. No, I don't know how we got there. Let me quickly. We're almost there. So that was a quick summary of the whole talk. I hope we have absorbed everything. So anyway, so we express reification as a macro, and then using that compile time staging, we gain source level expression of syntax trees and hygiene. So the relationship of hygienic macros and staging, that's actually been known before. There was a very nice paper by Ganz and others in ICFP 01. But I believe the ability to express staging through a reify was maybe also known, but I think we are the first to actually have coupled both of these things to get this bootstrap operation to say we have a very simple macro system, and then if the macro system gives us reify, then actually we can get a very nice macro system later on out of that. Okay, so I'm out of time. Thank you, and I'm happy to answer further questions. Anders.
I have one question about the reflection system that you have. So it is distinct and different from Java's reflection.
Yeah. Well, it's based on Java reflection because you need to get that to get the basics to work. It's
you also have sort of a reflection over the compiler's data structure, right? I mean,
yeah. So it's a different layer.
So
Can you repeat the questions, Martin? Sorry.
So the question was, well, the question is not quite finished yet, so let Anders finish.
No, I'm just curious whether you built like an abstract reflection layer that you then implemented over Java reflection and over compiler simple tables.
Right. So what we did is, so in terms of, I'm almost there. So what we did is we started. Sorry. Okay, yeah. Repeat the question. So the question was, well, how in what order did we do things? Did we design an abstract reflection system based on Java? So what's the relationship here? So what we did is, so the compiler existed first. The compiler exists for a long time. It uses the cake pattern that existed there first. What we did then to get there is essentially we pulled overall, I think, 15,000 lines or something like that out of the compiler into this universe. And that was a refactoring operation where we said, let's not redesign the data structures. The compiler has proven data structures. They work. They give us the information we need. We just put them in here. And then we added essentially the reflect runtime mirror to set, let's connect that thing here with the JVM runtime to do things like get the type from a naked Java class or invoke a method which needs to use a Java invocation and things like that. And then finally we built the abstract thing on top of that. So that was sort of the way we did that. But from here to here it was a pretty straightforward refactoring. We just pulled these things out. And again, because everything is type checked, it was fairly easy. So I used Eclipse and I just shoveled these 15,000 lines over there, and there were a couple hundred errors, which I just fixed. Well, they get highlighted in the editor, so you fix, and then when the errors were gone, it ran. So it wasn't a big deal.
So just one quick follow up. Then do you have implementations of your Expert of T that go straight to bytecode and execute it, or do you have to go through the compiler too?
We go through the compiler. That's actually another interesting angle. Is that what we have another thing in the reflection library is something called toolboxes, which contain essentially a compiler that you can use at runtime. And the compiler, the runtime compiler, it makes use of essentially the JVM reflection information instead of class files and source files. So it goes in here. But it's again essentially just the compiler, the normal compiler with some things abstracted out. And those things you use to actually, because when you produce these trees, then they don't have type info attached to them. They're just the naked tree. So you first need to use the compiler, the toolbox compiler, to get the trees, and then you can use the attributed trees to, again, use the toolbox compiler to generate bytecodes into a class which can then gets loaded at runtime and executed. So that's how we get execution capabilities in these trees. That's eval, basically.
I've been doing Scala on Android, and it's already pretty large and causing problems by just code size. This sounds like to do reflection, you need the whole compiler. Is this going to work in small embedded environments?
So that's a concern indeed. So what the answer will be is that the reflect jar that does the reflection will actually be a separate jar, and what happens is essentially at runtime, when I call reflect mirror, it will search using Java reflection now the reflect runtime mirror, which is defined in this full reflection jar. So essentially up here, the facade is in Scala library, but that's super lightweight because it essentially contains no code. But it will then, when I call one of these things, it will use Java reflection to actually get the reflect jar. And on some environments that might fail, like Android, that if you don't download a reflection jar, then that will fail. But you don't need to recompile or anything.
So reification does great in terms of from a minimalism standpoint, but 99% of the cases you actually do want to refile all of your symbols. So wouldn't make it sense to make reification the default course of action and allow people to actually evaluate when they want to? Sort of revert the defaults?
We thought about that because that's what most other languages seem to have done. Like I should say this is joint work with a student of mine, Yevgeny Burmako, and he came from Belarusia. And their Nemerle is a very popular language. So Nemerle had macros for a long time, statically type-checked macros. So a lot of the initial ideas came from Nemerle, even though the final design is completely different, I would say. So it was more a motivation than getting ideas. But Nemerle did it that way. So from my perspective, actually no, because I mean Scala is already a very, very powerful language, and in fact, if you listen to public reactions, then most are very, very negative about adding macros. So most people think we're crazy doing that, and in fact, we will probably put these things under a flag or something like that. That you're not. We will make it clear that macros will not be for everyone. That not everybody should feel compelled to write now their own macro-based abstractions. So the philosophy was then that if other people did macros for you, like assert or map on queryable, then using them should be as straightforward as calling methods. So no, but on the other hand, the same standard does not apply for people who want to define those macros. So we say, okay, these must be specialists. The least thing, if they get a macro system right, the least thing they should know is call reify. That was sort of the answer to that.
How much trouble does Java type erasure cause for this process?
Actually, in the end, none, because we have, well, to macros or to reflection?
Macros.
To macros. To macros, none, because it's a compile time operation, and we can lift all the type information into a type tag. The compiler knows it all. So at compile time, whether you have reified types or not at runtime doesn't matter. For reflection, of course, the problem is that we start off with Java reflection, which is very poor. So for a value, it will only give us the erased type, and that we can't recover. Unless, again, you have these type tags, which are the reified types, and they will actually help you recover them at the points where you want them. But you have to work for that. So overall, I think the type tag mechanism overall is very nice. It's a nice balance between reified and unreified types, because after all, we know they both have advantages and disadvantages.
You may have answered this already. Maybe I didn't catch it. I understand how reify makes it hygienic. That is, you're not capturing variables from the outside within your macro. But how does scoping work to keep symbols from leaking out of your macro? Because from what I understand, you're creating these AST, and you're monkey patching them in place.
So if you have an AST, then what happens is you have a reference to a variable. If the variable is defined in the macro itself, like with a valdef or a method def or things like that, then there's no problem, because the type checker will just redo the same binding. So I think the question is if the macro has a reference to a variable that's free in the macro, that's defined outside the macro. And that's indeed the tricky part of getting reified right. So there will be a thing called a free reference. So it will be essentially abstracted into a free reference, which gets the original value and its type and its name. And then you have to deal with that at the call site.
So the macro implementations, are they executed in any kind of sandboxed environment, or is it just all bets are off, your macro can do whatever it wants in the bowels of the compiler?
There's some sort of sandboxing. So the sandboxing is obtained by several components. So one is the compiler, in fact, is there are no static data to note of in a compiler. A compiler is just an object. You don't get the macro doesn't get a handle to the full compiler object. It gets a context, and in the context you abstract what you want to pass into the macro. In fact, there's a hierarchy of context, so a macro can demand to know more or less about the compiler, including a lot, where it can do all sorts of horrible things. But the nice part is it has to declare that it wants that by actually specifying a very rich context for its context parameter. The second sandboxing is, of course, if the macro throws exceptions, then these are caught at the expansion. And there's also a timeout that we say if things take too long, infinite loop or something like that, we will cut it off at some point.
But they can hit the file system or do other stuff if they want to.
They can hit the file system, yeah. There's no protection, yeah.
Go back to the debugging question. What does source level debugging feel like with macro expansion?
That's something we are currently working on. We haven't quite figured out yet. What we need to do, I think, is to actually have the result of macro expansion available as a sort of synthetic source file for the debugger, because otherwise it's very hard.
Sorry to bring back to hygienic macros, but was it a design goal to make unhygienic macros impossible, or is it just inconvenient to do so?
Oh, it's not impossible at all. You can write these syntax trees that I've shown you. You can do the design goal was to make them possible if you want them, to make hygienic macros possible if you want them. If you don't want them, then you can do whatever.
I might be confused about the direction the hygiene is broken in. Is it? I'm not familiar with how Scala in general, so I understood it to be that terms from the context could leak into terms from the context that refers to what is actually being compiled could leak into your macros. So, or no, the other way around. So your reify binding here might you might intend it to be bound in the context, but you're binding it to something that's happening in the compiler.
Yeah.
The other direction.
The other direction. You could do it also. So if you let's say you want to make a for loop where the argument here should be rebound to your for variable. That's a typical case of a non-hygienic macro. What you could do is you could actually erase the types in here and use the erase types. So there's an operation on trees to say erase all types. And then you could integrate the thing with erase types in your result type. And that would mean they would be retype checked. But when they're retype checked, essentially in the thing that you've constructed around them, you've constructed the for loop with the variable. So the variable would then be rebound to your variable. So,
So the macro is selected by the argument types that bubble up, and can you have overloaded macros?
Sorry, the
overloaded macros that are overloaded.
Overloaded macros would be.
And if so, how do you deal with satisfying type constraints, sort of upward and downward, through a macro?
The rules of method resolution. Let me just get this. For instance, here. So the rules of method resolution passing are exactly the same as for a method. We don't touch anything. So you resolve your method, you do overloading resolution and whatnot, and then if the result actually happens to be a macro, which you can see here at the right-hand side, then you will say, okay, now let's do the expansion. But it's completely orthogonal.
Completely orthogonal. And so there's a type satisfying step and type inference step before the macro is invoked?
Right. So the argument here will be type checked with actually the type that are given. So the arguments will be type checked always with an expected type. The result of the macro will be type checked against the declared result type afterwards, once the macro is expanded.
So it could be that types could not be satisfied after the macro.
That's right. That would give you a type error on the call at the call side.
Anyone else? Oh, come on, guys.
When can we use this? Is it into 10 trunk?
It's in trunk now. Yeah. What remains to be done is we have to clean up reflection a little bit, make it more user friendly. For the moment, there are too many sort of compiler internals that still leak, and some of the operations are too hard. Otherwise, we're in pretty good shape. Yeah. So what you've seen here, that should work. Yeah. Yeah. Thank you.
All right. Gone. Thank you very much to Martin.